Welcome back. Good to see you again. What's this? What's going on here? Calculus and optimization? Sounds like a big word to me, but actually it's quite a simple idea. I'll give you an example of using the word optimize. If you want to do well in this course, I think you want to optimize your results. The best way of doing that is to look at Huddy Matt's videos. Bit of an advert in there. But yeah, you want to do the best answer, if you like. And it can be what? What's the best answer? Well, sometimes you might want to enclose the maximum area, or you might want the minimum surface area of something. So the idea is this best answer is really coming back to what is the max or what is the min. So if you're running a business, you want the maximum profit but the minimum costs. So you might be working with mathematical expressions like that. Well, I would hope that you have seen something like this one up here before, and you've tried to get the best solution, that is the maximum area enclosed, without calculus. Just using what? What methods have you used in the past? You could draw the graph of the function which represents the area, or you could use, if the area function is a quadratic, the maximum minimum values of a quadratic function. So some of this hopefully you've done before. Let's look at this one. This is an interesting one. If we had a sheet of metal here of a particular length and width, rectangular, and we cut squares out of the corners here, we could fold it up into this little tray. And could you find the maximum or minimum volume of that by changing the size of the squares? What does that mean? Well, of course, if you took out big squares, you would have something like this size. Oh, yeah. Would that have a big volume or a small volume? Or you could go this way, or you could go even sort of bigger and skinnier and have little corners cut out. What do you reckon would be the optimum? Oh, there's that word again. What would be the optimum? No, I don't like that because it's running off the page there. We'll come back here in a minute. What would be the optimum situation, the best situation for the size of the squares to get maximum volume? That's what we're doing. We're playing around with possibilities and getting the best one. Okay, what about this one over here? Come back over here. What if I said I want a 1 litre container there? That's the volume. Well, it contains 1 litre, 1,000 centimetres cubed. And I wanted to find, let's say, the max, get rid of that one, the max surface area. Okay, a maximum surface area, maybe to cool down the contents most quickly, to expose it to the atmosphere or a cooling medium. Okay, so what about that? What sizes could we have for the maximum surface area? Well, the same thing, same idea as up the top here. Various shapes that we could make with a square base. We know there's a square base there, and various changes we can make there. All right, well, let's have a look at a more theoretical one. We're going to be doing a couple of these in a minute, show you how to do it and get the hang of it, if you like. So this is a more theoretical one. What's the biggest rectangle you can fit in? What's this? Well, 45 is an isosceles triangle, a right isosceles triangle, right angled at the top there, equal base angles, so it's isosceles. And what's the biggest rectangle you can fit in that if it's got a base of 20 centimetres? That's a bit more theoretical problem. But this is an interesting area of calculus and applications, and it's the last in the presentation of the new work. I've got one other presentation coming up for you which summarises some of the key points that we've looked at. And then, of course, some practice problems. But let's have a look at this one last area of applications, because it is an exciting notion now. Let's come down and have a look. Here we are. I've got a screen clipping here. This summary comes from Hayes and Harris. And I've put the heading Optimisation Techniques. What things can you do what techniques have you got to actually solve the problem? Well, we've already done two. Just get a graph onto your calculator and see where it's a max or a min. Okay, you could do that. Okay, hopefully you've done a bit of that back in year maybe 9 and year 10, certainly year 11, or you could use analytical methods. Analytical usually means algebra. So if it's a square, then you would use a vertex formula, wouldn't you? Remembering, let's have a look up here. The vertex is always given by x equals neg b over 2a. And of course, it's assuming the function is a nice one, y equals ax squared plus bx plus c, a simple quadratic. And here a would be negative, wouldn't it? Because it is concave down. So a little bit of revision there. So they are the ways we already have investigated. Or if you haven't, join in now, because we're going to go back over all of that. Or we could do, this is a new one, this one down here, use differential calculus to locate the turning points of a function. So when the function gets up into cubic land or quartic, complicated function, it might be looking something like this. Then you don't know these turning points. Okay, so you have to use calculus, because we know to find those turning points we will use the derivative equal to 0. So that's really, we're just adding this bit here to optimisation from your past study. So there we have it. You now can find the optimum value for any function, if you like. Okay, let's have a look now at what techniques. Well, hang on, I'm not going to actually let you see that yet, because I want you to pause for a minute and say, well, what would I do first of all if in this problem solving? What would be my first step? What do I need in all three of these techniques? What do I need to do first before I can get started on any of these? Okay, think about it. You might like to pause the presentation, discuss it with other people if you're in a group there. Okay, let's go on and have a look. Did you get it? Well, I think the first thing is to draw a large diagram. Sure, this is screen clipping again from Hayes and Harris. But here it is. You need a formula for the thing that you're trying to find the maximum minimum value, the quantity to be optimised. Okay, and the idea, if you're going to use graphical means on the calculator, you really want one variable in there. You know that on any of the calculators, when you enter y1, you can only have one variable in there. You can't have x's and y's in that side of the equation. It has to be an explicit statement, y in terms of just one variable. So sometimes there's a bit of algebra in getting that. And here's something important. You should write down what domain restrictions there are on x. Quite often, x has to be greater than 0. Okay, because it's often a length or something like that. This is in more the practical side of application of calculus now, not theoretical. And so usually lengths and stuff in our applications are not negative. So that's often one. But up to what value could x go in the context of the question? Just pause there in a minute. We'll come down and look at it down here. And then, of course, we know the max or minimum is when the first derivative is 0. Okay, so we have a domain. Usually the lowest value is 0, up to another value. And then the maximum or minimum may occur either when the derivative is 0 or at an endpoint, or at a point where the derivative is not defined. Okay, what does that mean? Well, maybe just come across here a little bit. We'll come across here a bit. And draw a little graph, and usually it's x greater than 0, so something like that. So here we might have a complicated function, in which case that's the local maximum, but we have a global maximum out here if we are allowed to go far enough out that way. And similarly, we could maybe beat this local minimum if we were allowed to go far enough that way. So we must come back over here. We must look at the values of the function at the possible endpoints in case they beat, I like that, in case they beat the local effect. Okay, so this domain statement is very, very important. Then, of course, you must show that it's a minimum. You could use a sign diagram or the second derivative or a graph. But just remember, in paper 1, you won't have a calculator. So if they ask you to show something algebraically, you have to be able to do it with sign diagram or a second derivative. Just remembering those things. We'll look at those things with some actual examples. And then write your answer in a sentence, making sure you specifically answer the question. Just remember, you have a question which is not really couched in mathematical terms. You want the maximum area enclosed or something. So you go into mathematical land, algebra land, with lots of x's and stuff. Well, that's not what the question asked. That was your tool you introduced to solve the problem. So you must specifically now say the maximum area enclosed, which could be enclosed, is, and this is the dimensions, or these are the dimensions. Okay, are you ready? Let's come down a little bit and have a look at this problem here. Okay, 40 metres of fencing material are available. Find the maximum area which is possible to enclose. Okay, so we have a diagram already, so we're lucky. A maximum area, so this is an optimisation problem. We want the biggest, the best value for the area, if you like. So we need a formula for the area. So we're going to say A of x. Because on our diagram already introduced for us is the fact that we have this rectangular field, if you like, up against a brick wall. This is equal, so that's x as well. We'll introduce x to mean something that can be varied within the context of the problem. Now, what's the area? Well, area of a rectangle is length by breadth, so we could call this y and come to the formula xy. I don't think in this problem that's necessarily good because we've introduced two variables, and you know what we want to do later. Let's use the first method. If we're in paper 1, in paper 2, we can use a calculator. But to put the function on a calculator, you need one variable. So can we go straight to one variable and say, well, hang on. Always look at the given information. You need to squeeze the given information to the max. I can do with calculus there, mate. But here, the given information says 40 metres. So if that's x and that's x, we've used 2x metres of fencing. This will be 40 take 2x, won't it? Okay, so maybe go straight to using a single variable. If you put in y, if you did use y in that hole, later on you'd have to say, well, y was what? 40 take the 2x. You'd have to do that subsequently, so we do get to this line, which is a single variable in our function. We don't need two of them. Okay, so let's now multiply that out. And so we've got 40x take 2x, 2x squared. Okay. There's our function we're going to play with. And if you remember up above, we just left it, we're going to do it in 3 different ways. The first 2 you have seen in earlier study, hopefully. If you haven't, let's do it together now. So the first thing that we're going to do to this is see if we can find the maximum. Has it got a maximum? Oh yeah, it's a quadratic. And A is negative, so it's concave down. Okay, it hasn't got a C value. Here's A, B, and there's no constant term. So it's all from your earlier quadratic theory. Let's now go and put it on the calculator. And if we do that, oh, there it is there, over there. So this is the calculator method using technology. And you would graph it. I've used the Casio here again. And you graph it, then you go Shift F5 and choose the option of the max here, and it pops on there, and gives you all the details. I've got derivative on from the setup menu, and so it confirms that the derivative is 0, right? Tangent's flat there, horizontal, parallel to the x-axis if you like, and when x is 10, y is 200. So we could state our answer there that we have the maximum area of 200 square metres when the rectangle has sides of 10 and 40 take 2 times 10 is 20, so it'd be 20 by 10 by 10, pretty much as the diagram looks. Okay, alright, that's one way. Okay, let's say you can't use technology, you're in paper 1, so here now let's use some algebra on this. This is a quadratic function. You might like to put it like this. Okay. Oops, I keep doing that. Neg 2x squared plus 40x plus 0 if you like. So A is neg 2 in quadratic land, B is 40, C is 0. We know it's a max when x equals neg b over 2a, so it equals neg 40 over 2a is neg 40, occurs at 10. And when x is 10, a is, substitute it back in here, 400, take 200, which is 200 square metres. Okay, and I'll state an answer right across the bottom here in a minute, because apart from the maths we must state our answer to the worded question, which was what's the dimensions of this field to give a maximum area. And then the new one. So this one's been done before, hopefully. This approach done before to find the best or optimum solution. Don't get frightened of that word optimisation. Sounds fancy, but the maths is pretty basic, isn't it? Okay, what about the calculus method? Here's the new one, because this is the one that's important now, isn't it? Why? Because you can't do this method particularly, you can't do if it's a cubic. And you may not have a calculator, and the calculator may not give you the exact answer when it's maybe in insert form, and it'll just give you a decimal. So we'll have a look at some of those later. Let's look at the calculus now. So we start with a function in a single variable. Notice that common approach, and then we're going to get the derivative. Okay, and find that turning point using the derivative. So there's our derivative. Do you agree? Derivative of 40x is 40. Derivative of 2x squared is 4x. Okay, so max, I like this, max or min when the derivative is 0. So let's put that 0. 40 take 4x equals 0. 40 equals 4x. 10 equals x. Okay, so let's draw a sign diagram for this. Sign diagram for a dashed x, and on the left, subbing in 0 into our derivative function up here, it would be positive, so it's going like that way, and subbing in something like 11 or 12 here, it's actually negative. So that gives you an idea that that is the maximum turning point when x is 10. We should check the domain. Notice we haven't done that at the moment. The domain for each of these. What is the domain for x? We'll put it across the bottom as a final check here. Domain is x has to be bigger than 0. And probably can't be 0. We usually put the equal sign in there, but that end condition of 0 does not apply. You'd have no rectangular field if x was 0, and it can go up to what? Well, it could be up to 20 apiece, wouldn't it? So what would that mean? It would be a long skinny field like this. Okay, something like that. Okay, and these would be approaching 20 and 20, using up your 40s, using up your 40 metres just on the length of the field with virtually no breadth. Again, you couldn't actually have the value equal to 20. So one should check at the end now that these values don't give you a high value. Now here you can see they don't. There they are, 0 and 20 where it cuts the axis. Obviously is a lower area because this is the area up here. So the graphical method sort of means you don't have to check the ends, but and here obviously with it knowing the quadratic. But later on we do want to bring this in, because where functions go up and down they aren't simple quadratics. You should check the ends. Okay, just mention one thing here. Let's come across a little bit. Come across here. We may not use a sign diagram to classify that turning point. Notice we don't need it here because it's quadratic. We understand a function. But you could use the second derivative. Right? The second derivative is what? Let's get the derivative of this line itself is -4 for all x. For all x. So what that means, if the second derivative is negative, it's concave down, isn't it? Which means it implies it's going to have a maximum. Second derivative negative is a local maximum. So either of these two methods for our more complicated functions coming up can be used to determine whether it's a local maximum or minimum. Alright, let's go back now to center screen and go on and have a look at some of these things now in harder functions. So this is a beauty. Let's state our answer before going on though. Therefore we have maximum area is, what was it, 200 square meters when the field is, what did we say it was, 20 meters by 10 meters. Okay, when x is 10 and the other side is 20, take 40 take 20, which is 20. So there's our final answer. No matter what method we use, we've got to come back from Mathland to answering the practical question. Alright, do you understand it? We're just adding some calculus on the end of some ideas you've probably seen before. Alright, let's go down and have a look at another example here, and this is from Pearson's now. So grab your textbook there. So they've got developing a general strategy. We've had a look at general strategy, and we had a look on our opening page of, had a look at this diagram, which is finding the maximum area of a rectangle inscribed in an isosceles right triangle whose hypotenuse is 20 centimetres long. So you need this first step, a large diagram, and they're saying let the length of the rectangle be x and the width be y, and we're going to have to get rid of that y or the x later, aren't we? We want a single variable because we've established that as a starting point for optimization problems. Here it is down here. Express the area as a function in terms of only one variable. Now it can be deduced from the diagram that y equals 10 take x on 2. Can it? I don't know. Well, let's have a look. Here this overall length is 20. Take out x, so these two little pieces on the end must add up to overall 20 take x. They're going to be equal. The symmetry of that placement, you're going to get a maximum area inscribed there when it's in the middle, if you like, placed symmetrically. So we will divide both of the 20 take x by 2, and so it's 10 take x on 2 for each piece, that piece and that piece. Okay, so we're making headway now with this. What's our next step though? Well, come back up here. See this won't do, will it? X times y. We can't have two variables there, so we need to get an expression for y in terms of x, and we've done it. Y here, let's have a look. If this is 10 take x on 2, and if you look at the symmetry of the thing, this is a right angle here because it's rectangular, that was 45, so this is going to be 45. So what that means is this is an isosceles triangle, and so that y equals that, 10 take x on 2. Bit of geometry there, and the same up the other end. So here, it's not that obvious that y is 10 take x on 2. We've found that one is 10 take x on 2. We've got to see that this is an isosceles triangle in here to show that this is y in here, and that is 10 take x on 2 also. Okay, so what's the area expression? X times 10 take x on 2, which is this creature. So again, it's a quadratic. Let's look at what are the limits on x here. Well, I'll just get rid of all this because it's getting untidy. What can x be? Well, it could shrink to nothing. Okay, so here domain could be down to nothing. Notice they've dropped out the equals, which is good, because if it was 0, no rectangle would exist. And what's the biggest x can be? Well, it could be up to 20, couldn't it? When basically you're drawing a long, flat rectangle. So this would be up to the maximum length of the rectangle would be 20. But it's strictly less than, because you can't actually have a rectangle when you've used the whole 20 there as its length. It would have no height then, it would be flat in the corners. Alright, so they are our restrictions and what we have to work with. So let's go and do, we'll use the calculus method. Notice that you could go from here and use the graph method, or you could use algebra on quadratics, because this is a quadratic. What we're going to do is practice our calculus, because there are going to be many functions in the future where you won't accurately be able to draw the graph, or usually you can, but you might want a particularly accurate answer, and with algebra, well, it's got to be a quadratic at this stage for you to be able to do that. So there will be functions in the future where you actually need calculus. Okay, so let's look at the calculus method. So the first step is to find the derivative of the area function, find what values of x is 0. So 10, so go back to this, the derivative of that is 10 take x. Put it equal to 0, and so that's when x is 10. Okay, analyse the function at x is 10 and also at the endpoints. Check that it's not doing anything funny. And you could use the second derivative test, or I want to put in here a sign diagram. Sign diagram for a dash x. Okay, sign diagram. So on here is 10, and then to the left, sub in a value to the left into 10 take x, and that's going to be a positive, and then to the right, putting in something like 12 in here, it'll be a negative. So we got a local maximum. And here you could use the second derivative test. So get the derivative, it's always neg1, derivative of the derivative, and therefore if the second derivative is negative, it's always concave down, and therefore it is a maximum. Okay, so either of these methods, second derivative or sign diagram. Sometimes the sign diagram is better because it's hard to get the second derivative, the function gets more complicated. We'll have a look at one of those in a minute. We should sub in the value at the endpoints. X is 0 and 20, and they just come down because it is a concave down parabola like we just did before, so there's no challenge there for the maximum value. Therefore it occurs when x is 10 and it's got a maximum area. Sub the 10 into the original function, not in the derivative, and you've got that. Okay, we should state the answer then. Well, they haven't. Oh, well, yes, it has. Yeah, we could unpack that a bit more and say the length of the rectangle is 10. The width is, what is that? 10 take x on 2, which is 5 and 5 centimeters, and the area is 50 square centimeters. Just put it in a bit more detail perhaps. Okay, let's have a look at another one. Are you getting the hang of it? That one was very similar. So here's a post problem. It occurred quite often in different ways. You might have, I think there's a common problem floating around where, come over here, where you have a pump house on the river and you want to pump water to 2 towns or something, where do you put the pump house so that the distance overall pipeline is a minimum? So that's the idea. Or 2 vertical posts, whichever interpretation, 2 heights, secured by a rope going from the top of one post to a point on the ground, and then go to the other post, and the distance is 25 metres between the bottom of the posts over here. Where should the point be? Here, so that you use the least amount of rope, minimum value there. Okay, so you draw the accurate diagram, and you can label the point R as I've done there, and you can, the optimum location for the minimum length this time, you can put it that as X or that as X. So let's choose the distance of the shorter post, or the shorter post as an origin of measurement, and measure it from there, so that's X, and then this of course is 25 take X, avoiding bringing in another variable Y. Okay, so then what's your length? Your length is A plus B. So here they're talking about that over here, labelling those 2 different lengths there, so that you can find the overall total length by adding them. Let's come down and look at that. The quantity minimises the length of the rope, which is the sum of A and B. So we've got to actually get L equals A plus B in terms of a single variable. So the idea here is that with Pythagoras' theorem, in this triangle here, A squared equals 49 plus X squared there, and over in this triangle using Pythagoras, we've got that. Okay, so not too bad. So have we got the thing to be minimised, which is the length, in terms of a single variable? Yeah, there it is there, A plus B. Okay, so we've got that. Now, I'm going to show you this way and then another way in a minute, but let's go on. What is the domain? Well, X can't be naught. They put an equal sign there, but the lower limit, which can never be reached, is naught, where you've moved R straight into the base of that smaller pole there, or it could go up to 25, and that's moving R right across to here. A bit nonsensical. So I would question putting in the equal signs there, because those end conditions, well, I suppose they can be, they can be met in a way, but that would give the second pole, whichever end you're talking about, no rope, so maybe a bit silly. Alright, so here we are. Look at this one. To facilitate differentiation, express L of X using fractional exponents. That's good. There it is. Then apply the chain rule. Oh, gets messy. And then let's put it, let's go through this. It's a half function to the 1 less power times the derivative of the bracket. Same here, half to the 1 less power times the derivative of the bracket. And then getting it over these, well, the negative half means over root x squared plus 9, and over root x squared take 50x plus 794. So then we've got to put this equal to naught. Very, very messy. Okay, because here what we're going to do is, if you put that equal to naught, you get that, square both sides, and then we get this thing, and then we can factorise it here, and we get these answers. Okay, now that's quite messy. There is another way of doing this, and that is to, up here, don't use L of X. Okay, well, if we go up to the top, let's have a look. I think, yeah, you can use L of X all squared. Now, it's not going to help here and find the minimum length when the minimum of the square is equal to naught. It actually doesn't help here, does it? Because we would have a product of 2 terms. But that isn't a bad trick. If there is a square root, let's say L of X was just root x squared plus 49, rather than use a half, you could say, because L of x is a positive value as a length, you could say max or min of L of x occurs when L of x, the derivative of L of x squared, is naught. So in other words, say that the minimum or maximum value of L of x occurs not only when its derivative is naught, or it's the square. And then of course you could work with L of x all squared, which gets rid of that root, square root sign. Okay, so you can use that since L of x is always a positive function here. It doesn't help much here because we've got the sum of two functions. But it's a bit of a mess, all of that, but you've got an exact answer. And if you go on the calculator, you won't necessarily get that exact answer. Can you notice this one's not in the domain, so we're not going to look at that. You can't have a negative length. So what are the values, the critical values, the values that we particularly need to look at? They're the ends of the domain, 0 and 25, and the turning point value x is 35 over 4. So now let's work out the values for each of those, and what we've got then is what is the minimum value at that point, 35 over 4, and it's 32.02. Okay, now they've got a comment down here about the second derivative test, because this, hang on, let's just go back up now, because this derivative is so messy, this is this line here, we're putting it equal to naught, it's going to be messy doing a second derivative for that. Okay, and using that to work out whether it's a maximum or a minimum. So what they're suggesting is you use a calculator, right, and draw the graph of L of x. Okay, but what if you're in paper 1, you really should have some justification for it being a minimum. Okay, so what could you do? Could you do a sign diagram? Let's go back up here. Where is the function? Here it is here, the derivative function. If we try to do a sign diagram for dl by dx, we know that it's a point there, 35 over 4, and we can't go past this here. Can't have this negative 175 over 6. So you could put in a value from this region. If you did, let's put in naught. This would be 0. This would be negative 25 over root 794. So that would be negative. Then if we put in something like, what would you put in here? Maybe something like 10. What is this here about? Put in 10 from here, and you could actually find that that's positive and do it that way. So you could actually do the sign diagram here if you had to justify algebraically or analytically that it was a minimum. Pearsons have not referred to that here. Okay, notice we do take this value and then just check the ends and take the minimum value of that, which is 32.02. Okay, you can do it on the calculator, of course, if that's available, but in paper 1, maybe a sign diagram this time to classify that, and then you can also check using the derivative on the calculator. Now, the idea here also is that the calculator may give you just decimals rather than the accurate rational value there for x, and what is it, something root 41 for y. So that's the advantage of using algebra. You will get the exact answer there. Okay, here's an interesting point that we're going to go on with now. The last two examples, all the ones we've done in fact so far, the extreme occurred at a point when the derivative was 0. Although this often happens, an extreme value may occur at the end point of the domain. Okay, so in other words, let's take a little graph here of something going up and down a bit. Okay, so that might be your derivative value. Okay, derivative equals naught there, but can you see over here, if you can go far enough up the domain, you may exceed that. Okay, so that's why we have to be careful to substitute in to the function the endpoint values of the domain. Okay, that's very, very important. Alright, let's go and do one that looks like that. Okay, so again, coming from Pearson's, they've got a good set of problems here. Example 15, an endpoint maximum. A supply of 4 meters of wire is to be used to form a square and a circle. How much of the wire should be used to make the square and how much should be used to make the circle in order to enclose the greatest amount of area? We've got two little constructions here, not just a rectangular field to get maximum area. Greatest amount of area, that's the max A. Guess the answer before looking at the following solution. Well, what would you guess? The area of a circle, what's the formula for that? Pi r squared. And the area for a square is just x squared or whatever, x by x. So what do you think? What would be the best combo of a square and a circle to give you maximum area? Okay, think about that. Okay, let's go and look at the solution now. Okay, so here we have it. We have a diagram making up a square, so called x by x, and then we have a circle where the radius r. Okay, so we're going to have to start introducing symbols, and we're going to try and get rid of all but one symbol, express the function in terms of a single variable. So what's the total area? It's x squared plus pi r squared. Now, we want the area as a function of a single variable, so what? We can put on the calculator, or we can use quadratic theory, or we can use calculus to find it. Okay, so we want to express r in terms of x, so I think it's easier to do that rather than x in terms of r. So what's the circumference of this circle? It's 2 pi r. Okay, so here then we've got this is 4x around its circumference plus 2 pi r has to come to 4 meters of wire. Okay, so always don't forget the given info. That's going to be important. Always squeeze all the given information so that you can get rid of one of those variables. And here we are, if we rearrange it, 2 pi is 4, take 4x, dividing by pi, dividing by pi and by 2, the 2 will cancel in the 4's, and we get this thing. So we have actually done it. It's not a nice looking function, but here it is, x squared plus pi r squared. There it is. There's our r in there, and we've got a single variable in our function, which is this thing. If you actually take out 1 over pi. Yeah. Okay, so you could leave it like this, or put it into this form here. That's expanding everything and putting a pi outside the bracket. Okay, what is the domain for a of x? Well, obviously the lower limit could be x could be non-existent. It would you just have a circle. Or how big could x be? Well, if you had no circle, x could be 1, so that the total around here contains the whole 4 meters of wire. Okay, so they are the n values which we're going to have to check. Okay, so if we get the derivative of this function, here we are getting the derivative of this function. It's a constant, and in here, derivative of that, 2 by that by x. Right, power rule, x to the n rule there. And then derivative of that is 0, derivative of this is -8. So we're going to put equal to 0. And here you can see the advantage of the algebra here. We have that derivative equal to naught when x is 4 over pi plus 4. If you did it on the calculator, it's going to give you that rounded off. So what are the critical values? Naught, the endpoints, then that 0 for the derivative, and x is 1. So you can sub those in. What Pearson's have done here is gone to the calculator and had to have a look at what's going on. And here we want the maximum area. We actually find that in this function we have a minimum value here when x is 0.5601, and the two endpoints, here they are both higher than that. And what's the greatest value? Here it is here. The area is 1.273, etc. when a is naught. That is all the y's used for the circle. Okay. And the actual value of the derivative, when the derivative's value was 0, we actually have a minimum. Okay, and we want a maximum area. So don't jump in and just assume. So what could you have done? We could have drawn a sign diagram back up here for this one, and got the idea that it's negative, 0, positive through that point, or concave up. Okay, what did the derivative actually look like? Up here, let's have a look. Here's the derivative here, this thing here. So we could have actually drawn a sign diagram for that at that stage, and sign diagram for a dash x, and subbed in values here. Subbed in a value to the left here, and if we put in 0, it would have been negative, and then subbed in a value to the right of 0.5, put in 1, and that would have been positive. And we could have seen right back there that that was going to be a minimum value. Okay, don't have to do that. We can determine that by subbing the values in, but that's another way of doing it, particularly if you're in paper 1 where you won't have access to the technology. So can you see that you must not assume when the derivative is 0 that it's a max or a min as required by the question. It may not. It may be the other thing, in which case the endpoints are the winners. One of those is going to win out as having the maximum area. And of course, what would the answer be if example 15 asks for the dimensions of the square and circle to enclose the least area? Well, we'd have this scenario there, wouldn't we? We'd have that absolute minimum, a local but also absolute minimum, when the x value was that. Okay. Alright, interesting enough, isn't it? You've got to keep your wits about you, but the maths is not that hard compared to some of the stuff we've been doing. Let's have a look now at another problem. Lots of words in this one, so we're going to have to unpack it carefully. We're nearly at the end to give you a chance to have a go. We're going to minimise time here. Okay, so we need a formula for time. Let's look at this one. Pipeline needs to be constructed to link an offshore drilling rig to an onshore refinery depot. Okay, the oil rig is located at a distance perpendicular to the coast of 140 kilometres from the coast. Alright, okay. So I don't know, you want to start picturing it. There's a picture down below. Okay, so here we are. Where is it? The oil rig is located just at a perpendicular coast of 140 kilometres. Okay, something like that. And the depot is located inland at a distance perpendicular of 60 kilometres from the coast. We don't know where that is. 60 kilometres from the coast. Modelling the coastline is assumed that there's a coastline. Point on the coastline nearest to the oil rig is 160 kilometres from the point on the coastline nearest to the depot. Okay, so this distance down here is 160. Okay, Okay, the rate at which crude oil is pumped through the pipeline varies according to several variables, including pipe dimensions and materials. So on average, oil flows through the offshore section at a rate of 9 kilometres per hour and 5 kilometres per hour through the onshore section. Assume that both sections of pipeline can travel straight from one point to another. At what point should the pipeline intersect with the coastline in order for the oil to take a minimum amount of time? Alright, okay, so it can come in here and then go down there. The different speeds of pumping in these areas. Okay, let's go and look at the completed diagram with all of that on it. That's a hard one to draw the diagram for. Here it is here. So we want to know, because there's different speeds of delivery here and here, where's the best place to put that point where it meets the coast. These are pipes here, pipeline. Okay, pipeline here and pipeline here. Alright, so that's our diagram, a hard one to draw there, lots of words. So let's say locate this point as x from that point there, x down from the point straight across from the oil rig. Okay, you could have let this be x, doesn't matter. Alright, so let's just tidy this up now. So if you say that's x, then what's this going to be? It's going to be 168, take x. Don't use y if you can avoid it, because you know you're going to need a single variable later on. Okay, now let's look at the length of this pipeline. Length of this pipeline, oh, Pythagoras to the rescue again. RC squared equals x squared plus 140 squared. There it is. And our pipeline in this region here is going to be, the length of that is going to be 160 take x squared plus 60 squared. So we've got those two lengths. But we're talking about time now. So we need a formula for the thing we're trying to minimise. The quantity to be minimised is time. So express the total time it takes in terms of a single variable. Time is distance over rate. Time offshore, that's this region, is distance divided by speed. And here, onshore, it's that distance, all expanded, divided by its speed. Okay, so the function for the time in terms of x, oh, what an animal here. Like that other one we had with two square roots added. So we've got our formula. We now look at the domain. Now, come back to the problem up here. What's the smallest value x could be? Well, if we put the pipeline just straight to land, that'd be the smallest value, so that could be 0. And that's a possibility. So we'll keep the equal sign in there. And what is the maximum value x could be? Well, it could go straight across the water to there. And so that would be equals 160. Okay, so x would be the whole thing there. Okay, so that we've set the problem up so that we can do a bit of calculus and also check the end conditions there. Okay, now Pearsons have said, well, you've seen the algebra from an earlier question with all those square roots. Let's not go through the pain again. So we're just going to go straight to a graph method here. Okay. Saying the algebra, finding the derivative is similar to what we did before. Okay, so graphing it, it does have a simple minimum. Here it is here. And that's the x value at which it occurs. And the minimum is that one there. Okay, so then we can state our answer purely off the calculator. Alright, so I think that's enough. Pearsons go on here. Talking about this, graphing the derivative of the value and computing any zeros in the domain. That's just checking it by graphing the derivative. So you could do that, but probably don't need too much. That's looking at where the derivative is 0, you're getting the same point. Probably just graph the function, keep it fairly simple there. Alright, okay, so let's have a look at doing some. Now, please go back and make notes electronically or on paper, whatever, hard copy, about the process from the earlier part of the presentation, we need to have a good diagram, see what's going on. We need to get a function in terms of single variable, because no matter what method you're using, we concluded at the beginning that that's what you needed, and then go through the process, get the derivative, check the domain, and into action there. Don't forget to state the answer in the context of the question, not in math land, not in algebra land, not in X land, but actually in the context in which it was asked. Okay, so here we go. As usual, I'll go through these, and at the end there will be the fully worked solutions. So here we have question 1 and 2. So pause the presentation, have a look, have a go. As you do a question, scroll forward, look at the answer, and then go back, so that you don't try them all and be making a silly mistake throughout. Okay, question 1 and 2. Let's go to question 3, 3 and 4. And question 5 there. Make sure you look at this hint up here. That's important. It's a bit of a different one, that one. So 5. Let's look at question 6. Interesting question. Question 6. Question 7. And that's all we have. This is a very similar problem to the one we just did. Walking and running, and so on. So, all right, are you happy? Let's go down and look at the solutions. Question 1. Question 2. Let's see if we can get it all on there. Question 3. Please work down the page. Pearsons are working across. Work down the page in maths. Easier to follow the reasoning. Question 4. Question 5. Question 6 now. And question 7. All right. I guess you're pretty proud of what you're achieving now. Some interesting work happening here, and you can see how to do quite complex problems. We haven't done very many hard ones here at all, but you've got the tools now. So in the final presentation, I hope you can have a view that later on. We're going to talk about all the techniques and do a general summary of all the differential calculus that we've done. All right, so enjoy yourself, work hard, and I'll catch you in the next presentation. Cheers for now.